presentation. Okay, so the issue now with the industry is fine. You have lots of methods available now. They are very sophisticated. But what happens really? Aircraft structure has so many details, lots of combinations of different stiffeners. Somewhere you will have a spar will have a cut. Along with the skin, you will have a rib, you will have somewhere a stiffener, different base sizes, and different geometries, all those. But everywhere you have to analyze for large damages requirement, like a discrete source damage. You cannot build the finite element such sophisticated model because they will consume too much of a memory, runtime, CPU time also when you are trying to analyze these damage problems. So it puts a lot of pressure on the resources if you have to make the models of each of the region which you want to analyze. So usually what will be done by the industry? That they would build some panels, test them, make the models, analyze using the FEM models, compare the test data, try to come out with that is a model verification essentially. So once you are confident with your modeling procedure, you are verified with the test data of some panels, stiffened panels, under tension, compression, all sorts of loading, whatever you want to design it to, and some environmental considerations. Then what you do, you try to analyze, because you can't test 100 panels also. But there could be, in your design, 100 scenarios for an aircraft, like a fuselage if it's composite, your wing, flaps, various components. So, there are more than hundreds of details which you have to analyze. So the best thing is one can do what you do as a parametric analysis. You test the coupons with a few parameters, geometric parameters like stiffeners, flange thickness, web thickness, like I've shown here actually, just representative. Suppose you have a stiffener like a blade stiffener. So thickness is the layups, stiffness, everything to it. So you make the model of, there could be head type stiffener, blade type, eye section, different type of stiffeners would be there, and different sizes. So you have to test if you get a confidence in your analysis tools. Once you have developed your analysis tools, then you will run, say, for various geometries, various parameters of the stiffeners, skins, and develop the residual strengths for each of those combinations. Using that data, there are now linear programs available, actually, we call response surfaces. Some softwares are available which can analyze dozens of parameters together and give you some kind of a response surface. Response surface is nothing but some kind of an empirical equation like what I've shown here in terms of various parameters. So suppose sigma r is the residual strength, which is function of various geometrical parameters. I've just considered like a coefficient, some exponents, which will come out whether it's a cubic or some 5-degree polynomial or whatever it is, various powers. That software can take care of it and analyze various parameters, because for each of that parameter, you have got the residual strength, and just put it into the software, it'll churn out some kind of equation for that surface. So once you have developed these equations, we call response surfaces, then the designers do not have to make any FEM models. They can just use these equations. So basically, it is an empirical equation which has been validated by test and analysis, both. And this is the procedure then one would follow. So when you are writing, say, design manuals, procedures, this is what the industry will do then, because engineers, they can't keep on making the models for every situation and analyze the situation.
Sir,
Yeah.
excuse me.
Sure.
Sir, how many such parameters we can consider, sir, in this equation? So T1 refers to what, sir? T2 and W1, is that the width or something like that?
Well, this is the width of this stiffener.
And T1, T2, sir?
T1 thickness of this flange, thickness of the web. You will have layups also, different percentages. I've not put all the parameters. There are many parameters. In fact, the softwares can analyze on 50, 60 parameters, even more these days. There are sophisticated programs available. I've forgotten the name of a book, actually. I had seen one of the book about this response surfaces, but writing a program might take, you people might be expert. Maybe you could search on Google the generation of response surfaces. So multivariate parameters. Because that analysis is used not only in aerospace, but lots of various places. And that's why some standard programs are available. Even in the production, for optimizing the parameters, those type programs are used.
Okay, sir, thank you.
So, any more questions? I think I would close this chapter on notch analysis. There's a lot which could have been done, but probably with the limited resources, we can't cover everything. But I have just provided you a background to.
Sir, this is, that delamination propagation.
Yeah, delamination propagation, what happens with that one? There are a lot of issues with that currently. So I don't think current practice is to use delamination propagation as we consider for the metals. The criteria, in fact, let me see if I added a slide over here, because you asked last week, a couple of weeks back, the question was asked. I think I might have put in the fatigue section, not in this one. So what happens, the delamination criteria, the disbond, we got to demonstrate the disbond of a particular length, which can be inspected during the inspection intervals, will not reduce the residual strength below the limit, and it will get stopped, arrested. That's the criteria currently. I'll show that in my fatigue or durability section. So I think I'll close that notch one presentation unless somebody has more question, but I'll discuss the delamination later on. Any more question on this notches, damages? If not, let me just close it and then open the damage tolerance. Even the damage tolerance, most of the part I have covered already during certification lecture. So what I'll do, I'll skip lots of slides from that presentation and try to be just quick. Fatigue, also same thing. I would just show only a few slides and not everything. Okay, so I'll just try to discuss a few slides out of this. I cut down a lot of material from this one because I don't want to repeat what is there in certification. Certification also we discuss the same things. Lecture. Okay, now I won't go into these are all criteria which I already discussed. Definitions I have covered earlier. Are you able to see this presentation? Damage tolerance or no? Hello?
Yes, sir, we are able to see.
Yes.
Okay. So these slides already I had shown earlier about, okay. Now, I showed, of course, in my certification, why damage tolerance. Damage tolerance is a design philosophy used in maintaining the structural safety of the aircraft, of course. And the flyable damage or crack philosophy is the damage tolerance evaluation is means of providing an inspection program for an aircraft that is not expected to crack, damage under normal circumstances, but may crack in service due to inadvertent circumstances. So essentially, damage philosophy or crack philosophy, which is true for metals, is to determine inspection program, essentially. In composites, we don't care about that because we decide no crack growth damage, no growth of damage. So that crack growth doesn't arise here. Some of the slides which you will find, I've just combined the metallic and composites just to give you a feel. If damage is found in primary structure, they must be repaired before further flight. So that's a requirement. Exception, engineering evaluation must show that the strength will never be degraded below ultimate strength during flight with known damage. This evaluation must consider slow, stable tearing during an ultimate load application. So damage tolerance diagram. Now this diagram I've already shown earlier, which was a bit complex. So I thought I'll simplify rather than showing a complex diagram, which becomes confusing. So I just simplified this one. The message is same, type 1, type 2. Another thing which I've done here from the previous one, I defined the category 1, 2, 3 based on AC 2107B. But why I have changed to type rather than the category? Because category I'm defining according to Boeing for another purpose here. So I thought, let me change it and return everything else same. Undetectable, detectable, readily detectable, immediately obvious. I won't explain that. I've already explained. I've already explained this table in certification. Okay, so damage definitions and sizes, BVID, won't go into the details of this.
Sir.
Yeah.
Excuse me.
Yes.
Sir, can you please throw some lights on the inspection program? How we can do the scheduling of the inspection program after how many hours or something like that?
For metal.
For metal as well as composite, sir.
Okay.
For metal.
Yes. What I will do, I have already sent the references from Boeing, excellent papers, and it will be difficult for me to just because it's a very complex program, inspection program, supplemental inspection, the way Boeing uses. And the references which are published in the open literature by Goranson, he was the chief for structures damage technology at Boeing, and masterpiece, reference is available, which I've already sent, and I can send again, Goranson, which I'll just show now. So you can look into that because it's difficult for me to provide the inspection plan in this lecture. But if you have some issues, you can refer to me later on. For composites, there's no inspection plan that way. You don't consider the
okay,
rate
for
of
composite,
growth.
it's not considered, yes.
Yes.
Because there we only consider SN approach, only stress life approach, set life approach.
That's right. So you are from NAL, is it?
Yes, sir. Yes.
Okay.
Yes, sir.
What's your name?
My name is Pradeep Kumar Sahu.
Okay.
PK Sahu.
Okay.
Sahu. Pradeep.
Right. Now, this BVID damage, what you are seeing on the screen, I had a couple of days back, I had written to Kotesh and Dr. Ramesh that NAL is using the criteria as 1.2 to 1.3 millimeter. And from Boeing publication, which I've put here, say damage size based on alpha set, is in public domain. Again, I sent this paper to NAL also, behaviour study to Kotre, I took 3 or 4 days back, and to Professor Dinesh, where the damage size normally is 0.25 to 0.5 millimeter for BVID, which Boeing, I mean, according to this one, Boeing considers that's what it is. But anyway, that's immaterial.
Yes.
The undetectable damages, again, I won't go into the details of the earlier I've explained. This is just a picture I had taken from one of the Boeing references. This is in public domain, so I could provide this picture to you. And this one also I have earlier discussed, the delamination or disbonds at the interface, which you need to consider for initial damage, that is undetectable damages like half-inch by half-inch flaw. And but military aircraft consider like a 50 millimeter, 2 inches diameter, according to JSSGG. But this again I have discussed earlier, so I won't go into the details. Surface scratch, I have visible impact damage criteria, which is defined by the dam depth at least a millimeter. Over millimeter, it becomes visible, and there's no energy cutoff when you are trying to generate this visible impact damage. And the residual strength limit is P limit for this one to support the limit load carrying capability. Here I've shown some pictures from, again, this is in public domain, but from Boeing. Some damages for visible impact damages picture. Okay. I've already considered that large damages like a hose, again, it's a organization dependent. So this is detectable and readily detectable damages I've discussed earlier. Stiffened panel I've discussed today, and therefore study the requirement. Won't discuss that now. So your question was regarding the delamination or disbond of bonded interfaces. So I've just shown a picture here. Suppose you have a stiffener and this is skin and there's a bond line. Okay, now the requirement is, if it's a critical part, damage to a bond line due to manufacturing, environment, or accident must not propagate to a residual strength condition of less than limit load. So that means, suppose the maximum length which you can allow is L, and it should not propagate beyond that if the residual strength with this bond is limit load carrying capability. You cannot allow it to propagate further. So design with arrestment features such as limit load strength is maintained with a complete disbond between adjacent arrestment features, residual strength P limit, after 2 inspection intervals. So this is the requirement. Now your question is whether we can use DA by DN type of analysis. You can do it as long as you are confident in propagation prediction. However, again, you have to show that in 2 inspection intervals, that damage which is propagated will not go beyond your prediction. So still there are issues about the reliability of the prediction of the delamination propagation by using a DA by D and a function of strain energy release rate. I had sent the paper, I think last week or so, and a reference to Professor Dinesh. You asked me about some reference on the delamination propagation. I don't have the electronic copy of that reference, but it is in ASTM STP 917. So any question on this? Delamination issue? Because this is the condition currently we have to satisfy.
Sir, for such panel bonded joints, so we have to do the DT damage tolerance, yeah, and also you need to find out the residual strength and inspection interval. Also for this we can do for such.
No. What happens with the inspection intervals? You are not deciding the inspection interval. Now, suppose you say, you decide, okay, every year that has to be inspected. The industry will not like it.
Okay.
Because I'll show the inspection intervals in the fatigue slide, say Boeing. So what happens about the inspection intervals? Normally, the industry will decide, okay, we'll allow 2C checks after 6 years, 4C checks after 12 years, or 10 years. So they are pre-decided, and then a designer will have to work out so that within that inspection interval, the damage cannot propagate and cause the residual strength to be below limit. And that is where it's other way. Rather than you providing the inspection intervals, because as a designer, if you are free to provide the inspection intervals, we will say, okay, every 3 years the airline should inspect it in detail. But airlines are not going to accept it. It's too expensive. So inspection interval is quite complicated issue. And that is why you should read the papers, which I can again send. In fact, I have sent to NL basically the same papers, all the papers recently to Kottresh and Dr. Ramesh.
Okay.
From Boeing.
This is with Mr. Kotres.
Yes, Kottresh also has a copy of those Boeing papers.
Okay.
So ask him. If not, I can send you again. If you send me the email.
Okay. So mine is only PKS. Is there anything where I can mention chart box?
Pardon?
PKS @nl.res.in, sir.
Well, I won't remember. Send me the email.
Okay. I have your email ID. I think during your lecture, okay, we had communicated. I think I will send you email, sir.
You send me the email. I'll send you the references. You send me the question, whatever you want. I'll provide the material.
Okay, sir. Fine,
That's the best way because I won't remember.
Yes, sir. Thanks a lot.
Yeah. Okay. So, buddy strike. I've shown this earlier. I won't go into the details. So, lightning strike criteria. Again, I'll skip all that. And now, so I think I showed this slide earlier, but again, I can repeat this and to clarify about the inspections. What this slide is showing, the strength versus time or cycles. And this is the limit load, and this is ultimate load capability. Suppose this is a metal slow crack growth. So the crack is growing, and then after some time, the residual strength with this length drops, and it's slowly, but really it will be picked up a short duration below ultimate load, and the damage has to be repaired and restored. In composites, sometimes it may so happen that instead of slow crack growth, the damage suddenly occurs. Damage initiation propagation load capability drops. Now, you can't afford to have, for a long duration, possible long-term below ultimate not acceptable without repair. So for a short duration, probably it might be acceptable, and then the repair has to be done. Now, this is sudden jump. Another basis of inspection interval, no damage growth. Here we are considering no damage growth at all. And see here is the same picture which is there from the previous one. Ultimate load, limit load, critical crack size is suppose this one, or the damage. Threshold of detectability. So damage initiation or sudden. Again, of course, we are using a no crack growth philosophy, no damage growth philosophy. And then what happens? Suppose the damage occurs, and this is a critical size. That means here the residual strength will be limit load. So then sudden damage growth, there's residual strength reduction, which is shown by this one, of course, this is residual strength. Again, below ultimate. However, node growth inspection interval may be less than 50 flights. Now think I've just put a inspection interval. You are not having any inspection interval defined like a 50 flights or 60 flights. I've just said here, this damage should be picked up during walk around inspection within less than 50 flights, say. This is just arbitrary figure I'm putting. So the moment it is all in a few flights, so the moment it is picked up, this damage has to be repaired. That's a condition. Damage must be repaired. Not acceptable without repair. So these are conditions here. This another chart just shows slow crack growth, which is true for the metal. So basis of inspection interval, you asked me the question. This is the basis of inspection interval, crudely. That you have a threshold of detectability. This is very simplistic picture, but when you read the Goranson's, that is paper from the Boeing, it's far more complicated, the way the inspection intervals are decided. So threshold of detectability, that is what it is mean, that you can see this crack. Below that, the crack can't be seen. Okay. So then the crack grows, suppose. What you see this line here, the residual strength capability is the limit load carrying capability. So this period from here to here should be double of two inspection interval. The way we consider, okay, the inspection interval is two inspection intervals. Okay, but one missed inspection, and that is why you are doubling it up, because it has to be considered, okay, in first inspection interval, it may not have been picked up. So in the next inspection interval, it may be picked up. That's why you design it for double the inspection intervals. So inspection interval is time between high probability of damage detection and residual strength below ultimate. Any detected damage, residual strength less than ultimate must be repaired or part must be replaced. Generally, the maintenance inspection intervals are defined by the manufacturer, and designer need to design the structure considering defined inspection intervals ensuring damage tolerance philosophy. And this is what I've just quoted from some Boeing reference, the inspection checks. Check is external 2C check. So 2C check, that is external inspections we call. No inspection behind panels. You don't remove any panels and look into internally. Just outside. 767, 3 years. 777, 4 years. 787, 6 years. That is a 2C check. external only. But 4C check, which is a bit detailed one, typical D check or heavy check, significant access required. So this is internal, removing panels and internally looking. That's 12 years. So suppose you have a detail which is hidden. You can't open it and look into before 12 years anyway. Airlines would just believe Boeing that they don't have to do anything for 12 years unless something is visible outside or malfunctioning of some detail, some failures. Otherwise, detailed inspection will not be done. Inspections are very expensive for airline, detailed inspections. So that's why, and why 787 is having much larger inspection interval, because they have been able to design it with the composite structures, not like metals which require frequent inspections. And that's the reason actually they have been able to increase the inspection intervals for 787. Okay, structure detailed damage tolerance requirement. I won't go into the details. I have already discussed this.
Sir,
Yeah.
how many flight hours, sir, in 12 years? 12 years is the life, sir?
Well, the thing is, it depends upon whether it's a short, flight version or long flight version.
787, yeah.
So 787, if it's a short mission, it's about, I think, 45,000 flights or 44,000 or 44,000 flights. And for a long range, it is much less number of flights. But what happens to fatigue cycles would be dictated by the short mission cycles rather than the long mission, because number of takeoffs and landings will be more for the short mission. So short mission more becomes more critical for the fatigue than the long mission.
Okay.
Okay, now this reference, what is there in this, what you see on the front by Steve Chisholm, I think he's now currently engineering vice president of Boeing. Anthony Ruffin, he was an STT earlier, he retired several years back. Brad Chapman and Quinn Benson. So there's a paper from public domain, 40 years of structural durability and damage tolerance of Boeing airplanes. Very interesting about Boeing, damage tolerance philosophy and durability, to read this paper. Again, this paper I had sent to Professor Dinesh as well as to NAL, Kotrish. Okay, when I said category, damage of category, now Boeing has defined the categories of damages in a different manner. That's why it changed to type. So here, this is table what I just wanted to discuss so that you have some idea about which component needs to be assessed to what level. So damage tolerance philosophy, this is Boeing philosophy. Secondary structure, category one. Category one is the secondary structures like non-PSEs, where Boeing's design philosophy is designed for safe operation or loss of function. They don't consider large notch damage tolerance for secondary structures, and which I did discuss during certification also. There's no requirement from FAA for that. Technology controlled method, continuous safe flight. Basically, the only safety mechanism is that suppose the part has failed, like flaperon, which is a non-PSE structure for 787, or spoilers. It is designed just for a safe separation or loss of function. And suppose that component fails, it does not jeopardize the safety of the flight. And so like wing spoiler segment, safe separation or loss of function, that's it. No damage tolerance for the large damages required for these ones. Category 2. Category 2 Boeing defines is type of structure where damage obvious or malfunction evident. That is very large damage can be seen from a distance just during general visual inspection from outside. Or it could be some failure of fitting, some malfunctioning of control system. So basically, is the damage obvious or malfunction evident? So what this requirement is, technique of ensuring safety, adequate residual strength with extensive damage. So large damages when we are considering, so just you have to design with that large damage for the residual strength requirement for the regulatory requirement. And that is technology control method, residual strength, basically for that damage. Typical structures like a typical wing, skin stringer, surface, fuel leak. Fuel leak is basically a obvious damage because if fuel leak is occurring, that means there must be damage and then it should be repaired. Fail safety required for category 2 and 3. Additional WFD analysis for certain category 3 structure. Now category 3 I'll show next one. What is category 3 type of structures? The damage detection by planned inspection. Now what we are talking of, some hidden, like suppose you have a stiffener to a skin joint, which you can't see from outside, the crack in the metal. And so for that, those type of structures are defined as category 3. Once again, the details of this is given in either one of the Goranson's papers, the Boeing papers which are there, they have these details. It's all defined there. So those of you who are interested, I would advise to read some of those Boeing papers. They are real classical papers, and one of the best information available is from authentic organization. Fortunately, they are in public domain, so I've been able to share with you. It talks about all the philosophy of Boeing. So technology control, again, residual strength and crack inspection program. That means crack propagation and inspection program. In this, there was no crack inspection program here for category 2 structure. And this is the difference. Planned inspection over here. And all primary structures not included in category 3 and 4. 4 we'll discuss your safe life approach. Okay, so that's the difference between various categories of the structures which Boeing defines as. FA, damage tolerance approach, is more general, but this table, which I have picked from Boeing reference, is very useful to categorize the structures into different category for the inspections, determinations, detailed inspection. Okay, category 4, Boeing defines category 4 is safe life structure, which is like a landing gear structure. Safe life. Not all the structures are designed with safe life. Okay, now primary structure damage tolerance philosophy summary. I've already discussed this. I won't discuss this slide, but I've just prepared this slide in order to make it more obvious, like category 1, 2, 3. That damage obvious for malfunction evident residual strength, damage detection by planned inspection, residual strength, crack growth inspection. So in summary, this gives the picture of all 3 types of damages. Oh, come on.
Sir,
this is wrong. Let me change it. I'm sorry. This is category 2. Category 3. Sorry for that. I might have just copied wrongly. Oh, sorry. I'll send this revised copy tonight. Okay, your question, you were asking some question or?
Yes, sir. My question is that fuselage comes under which category, sir? It will be category 3, fuselage, metallic fuselage.
Yes, we are talking. In fact, we are talking about metallic basically structure here.
Okay.
So
Fuselage, all the components will that
again,
come?
it depends. So category 2, suppose category 2 is damage obvious. Obvious damage, suppose you have a large damage which is visible from outside, that panel will, because like suppose you have a skin to stiffener and the skin panel broken, outside it can be visible, suppose the crack, large crack. But
Yes.
if you are considering the stiffener which is hidden inside and the fasteners over there, the cracks are initiating from that. The clear pictures actually I should have shown, they are given in that those references. Which parts are visible, which parts are not visible, when the cracks become visible, those stiffened structures for the metal. Very interesting. So again, you can look into that. So your question was fuselage. Of course, fuselage parts, some of the parts will be in category 3 and some will be category 2.
Some will be category 2. Category 2 and 3 will cover the fuselage for all the
Yes.
components.
Yeah, they will cover everything. Category 4 is only safe life.
That is landing gear. Yeah.
That's it. So all the structures, essentially all PSEs, will be covered by category 2 and 3. Category 2, there is no inspection required. Is malfunction evident or obviously visible outside? Is the category 3 for which you have to worry about the inspection intervals. And the way Boeing defines, which is defined in that paper by Goanson, is a very complex process. One could simplify. Of course, they have developed complex methods, but simplification would be the diagram which I showed you for the inspection interval. Slow crack growth, if you can determine that, and evident during inspection intervals, that's how you will do. Okay, here damage tolerance elements. So basically, what damage tolerance contains is damage threats, types and sizes, probability of occurrence, residual strength. There is another element of damage. That's what you do. Damage growth, life assessment, residual strength, inspection plan. So these are 3 entities for damage tolerance, basically. Inspection plan, residual strength, and damage. Durability. I'll consider durability in the fatigue chapter. Damage tolerance objectives. I won't go into the detail. The purpose of damage tolerance objective is residual strength, of course, per 571. And second is the determination and inspection intervals. Now, this is for metal, of course, this one. So that's why I've said, okay, metals only. I combined here some of the slides for the metal also because the question would come up, okay, what is the difference between metal and composite? So this is getting a mixed metal and composite in this presentation. So widespread fatigue damage evaluation, mainly done for the metal, not for the composite. Okay, damage tolerance compliance approach, analysis and by test. Test uses the building block approach. Now, I'll not go into the details of this because I already shown earlier during my certification. That's why. So damage tolerance analysis, static loads, residual strength. And this is what we do in composites. In metals, fatigue loads, then damage propagation is considered in the metals. In composites, as I've been always emphasizing, we can't consider the damage growth, except probably the delamination, which again, as I said now, I would not consider currently. So inspection, determination, inspection involves widespread fatigue damage, metal only. Methods of test analysis presented separately. Thank you. This is this is quickly, I just wanted to show most of the things for repeating, but a few things I put additionally, the Boeing criteria. That's why I thought, let me just show it to you. But I would still recommend to you to just flip through those references from Boeing. If you don't have access, anybody doesn't have access, I'll send all the references. There are 4 or 5 references which I'll send again if somebody wants. But they are very interesting. They provide a full picture about the Boeing damage tolerance philosophy. Okay, now I can just, okay, what I'll do, I'll just show the paper which I was referring to from Goranson, one of the papers, there are a couple of papers. Are you able to see the screen, this paper?
Yes,
sir.
Okay.
Damage tolerance, yes.
Now, this person, Goranson, he was at STT, retired several years back, of course, but this is an invited lecture which he had given in 2007 keynote presentation at Netherlands. I'm just trying to show, I'm not going to the details, there's 58 pages. So you were asked damage tolerance principles. It describes the damage tolerance principle beautifully here. And structural strength, inspection criteria. Now I'll show you how difficult the inspection criteria projects the way the Boeing is working. All here it describes the damage lengths normalized. I won't go into details. What I will show you. So this slide, like a structural strength, WFT detection period, local damage, crack growth, technology standard. Now some details it shows how the crack detection is done. There are further pictures showing, let me just show. Inspection criteria. We use the damage tolerance rating, in fact, DTR. Threshold, but fuel safe fatigue evidence. Yeah, it tries to explain here inspectable crack lengths from outside, from inside. So like this. I won't go into details, just giving you this idea what this paper contains. And there's a lot of theory given in this one. Relative crack length, cumulative detection probability. So they will go by the probability of detection. And what I was saying, it's a very complex math, which Boeing had developed based on damage tolerance ratings. You have to read it to understand. Okay, it's pretty long paper. It's about 58 pages. Another paper, which is Boeing Technical Journal, 40 years of structures durability and damage tolerance at Boeing airplanes. Very interesting paper. Again, I'll close. Another paper I'll just show you by Al-Fawcett, Boeing Composite Airframe Damage Tolerance and Service Experience. It provides the criteria. Some of the slides which I have shown in my presentation have been taken from here. But again, this is Boeing philosophy for the composite structures damage tolerance. Al-Fawcett is retired several years back. He was the authorized representative for composite structures. He was also a contributor to Millennium 17. He had a lot of experience. So again, this is an interesting paper. Okay, now this was a good, again, showing the papers. Let me just open the next chapter, fatigue, and a few, maybe about 10 minutes discussion on that. Again, I won't go into the details. of fatigue. So quickly, only as such, there are not more than 10 minutes for the discussion. I want to finish it today. Okay, fatigue of composite structures. I won't go into the details of this. What is fatigue? Again, I'll just skip all this. Just try to show here, the typical metallic fatigue behavior, the typical composite fatigue behavior won't be discussed in the detail. This slide I had shown during my certification, the difference in the metal and composite SN curve. For composite, the damage is not as a self-similar crack growth, is some mixed damage, while metal is a single crack, which is deterministic slab crack growth. Here, just some example I had plotted here showing the difference between aluminum and composite for the damage. You can see here, the aluminum is very steep SN curve compared to the composites. So that's the advantage of composite are better in fatigue. Initiation progression, now I'm going to. So there was a discussion about this Paris law. Of course, this is for the metals, acceptable dA by dN in this zone, and this is a nucleation phase, unstable phase, which is standard. In fact, so any book you will find this. And dA by dN is represented by Paris law. Won't go into the details unless somebody wants me to discuss the details. The reason I'm just going because I wanted to finish it today. There's not much time unless I extend to another lecture. So damage growth, metal, self-similar, dA by dN, C delta K, and composites, non-self-similar except in delamination, difficult to define crack growth relation except delamination. So damages in composite grow like this. Only the delamination can go like this. Okay, now this damage growth in composites. I've shown some picture here. You have a 0, 45, minus 45, 90 layup. So when you start loading it, 90-degree ply cracks, and then later on 40-degree, 45-degree plies also will start cracking. And then 45-degree ply and 90-degree ply cracks will try to merge together. And then what will happen? There would be interlaminar separation, which is a delamination occurring. It can happen during static and fatigue loads. So gradually, so delamination occurs, and then what happens? The laminate gets weakened gradually, and then fibers start failing, and so a fracture occurs. That's the end of the laminate failure process. This is just a schematic, very interesting diagram of the damage accumulations in the composites. This just shows some picture of the laminate which I provided, say again 0, 45, minus 45, yes, 3501, dash 6 with the open hole. Fatigue, TT, tension, hole diameter 6.35 millimeter and 26 millimeter coupon. 75,000 cycles, 150,000 cycles, 200, and you can see how the damage is progressing. All the damage is going along the load direction. So this is the difference between the metal and composite. Damage growth composites. It's very difficult, as I've been always emphasizing, to predict how the damage will grow in composites. That's why there's no reliable method, although there are hundreds of people have tried to put various models using the stiffness reduction, damage accumulation, using a power law, Paris law, which may work only for the delamination. None of the methods provide the fatigue life for composites due to complex failure modes. Next slide. I've just tried to show schematically life prediction, the mechanistic based, like damage initiation, propagation using the strain energy release rate, which is for the delamination only, the relationship which we have been talking about, dA by d and some C, and this is a function of strain energy release rate. Here, this is a phenomenological, exact mechanistic model is not possible. Damage is change in the stiffness or strength, that is dd, some damage as a function of the number of cycles, C, function of ED, that is D is damage, E is the stiffness. These models, a lot of people have tried, but nothing works successfully. And in practice, we can't use any of these models. The only thing which has been used is this for delamination. So delamination, basically two modes, mode 1 and mode 2. Mode 3 is not tested. Usually we consider mode 3 toughness is the same as the mode 2. Won't go into the details. Mode 1 delamination equation here, mode 2 delamination. Now dA by dN, somebody asked a question last time, showing the functionality. So dA by dN is a function of C, which is a parameter, again, function of the G raised to the power m. And Fg is defined as under root G max minus under root G minimum square, where G max is maximum strain release rate, minimum strain release rate. Stress ratio is defined as P minimum and P max. So what has to happen in order to generate these M and C parameters? You test the coupons, and based on the crack growth from the coupon, you can generate these parameters for that characteristic of the material. Again, I'm not going to the details of that. So one of the references where some work was done was by, I think, Street and those people, I don't remember the name, but I can send the reference again, which might have to, you find it from ASTM 971, if you have at NAL that ASTM. I don't have a copy of the paper. But there was some PhD thesis from internet I downloaded. You can look into that, which again, I can send the reference to that. Okay, now challenges for fiber, fatigue evaluation and composite, complex damage mediation and propagation events, fiber splitting, fiber autometrics, matrix cracking, delamination, fiber bridging. So various damage phenomena may occur, which causes the issue in terms of making the damage propagation as deterministic. You can't determine it. Again, other parameters, fiber matrix, material reinforcement type, all these various parameters. Again, I won't read it. So composite fatigue issues, prediction of useful life for an applied load, difficult. Residual strength of number of fatigue cycles and damage growth with time, which is not possible. Fatigue evaluation, composite structures, composite analysis criteria, no damage growth, current philosophy, no reliable method to predict damage growth. Slow growth, limited application, which is delamination. Again, I have been emphasizing we don't use it. Fatigue, no damage growth, philosophy, manufacturing anomalies and undetectable damages shall not grow during lifetimes. Visible damage not to grow for 2 inspection intervals. This is the criteria which is substantiated by coupon subcomponent and component test. No theoretical basis. Composite fatigue behavior, some charts. Some charts I have just plotted from some reference from ASM 21. This is showing maximum stress versus N cycle, that is life. If you have a 0 degree, this is for all R equal to -1. So if you have 0 degree laminate, it has a very good fatigue behavior. As the percentage 0 degree is going down, that is, are putting more 90 and 45s, the fatigue behavior decreases. Naturally, because static allowable also comes down and fatigue allowable also will come down. with a percentage 0 degree fiber. So this is what happens with various laminates life. Here, this is a very interesting chart. Basically, what it is showing, laminate fatigue strength divided by unidirectional fatigue strength, unidirectional laminate fatigue strength, unidirectional fatigue strength, and laminate fatigue strength. Basically, it will depend on the percentage 0 degree fibers versus laminate static strength divided by unidirectional static strength. There's a good correlation between the static strength and the fatigue strength for the composite, which is not possible for the metal. Metal doesn't follow this behavior. So if you have the ratio of the static strength to unidirectional static strength, that is, you have 0 degree static strength, this is 0 degree static strength, and this is laminate static strength, quasi-isotropic, suppose it's 0.4, same ratio for laminate fatigue strength divided by unidirectional fatigue strength occurs. Very interesting chart, which I found from this reference. When you want to consider, suppose you don't have significant amount of data available, probably you could extrapolate, okay, I know the fatigue static behavior, then I can determine the fatigue behavior also similarly. Very interesting. Okay.
That means both will be same.
Well, this is what is shown. It's not necessarily for every, I can't prove it, but essentially, based on this data from the ASM9, this is for T300 5208 material. This is pretty close. As you can see, suppose 0.4 here, 0.4 here, and say 0.6, 0.6 approximately. But in industry,
thickness will be maintained.
Well,
0 degree or laminate of a different stacking sequence, thickness will remain same. For same thickness, this strength plot, sir.
Well, I'm not. It should be similar thickness. In fact, it may not depend upon significantly on thickness unless the coupon buckles, it should not be a function of thickness. So you make the coupon so that it doesn't buckle when you are cycling it. So some thickness like a probably 3 millimeter, 4 millimeter thick coupons you might use. And essentially, I can tell you thickness. Suppose they have tested 0 to plus minus 45. How many layers are there? 2, 4. That is 4 layers. 2, 8, 16 layers. And normally T300 5208, the ply thickness would be around 5, I think is maybe about 5 thou. So
0.1.
Pardon?
0.15.
Yeah, about 0.1 approximately 0.125. So 0.125, 8 layers. This will be 1 millimeter is pretty thin.
Yeah.
You know, I'm not sure. They won't have been able to apply for this thickness R equal to -1. It might have been for positive tension. It doesn't say. I'll look into the real reference. It should be tension because you can't apply such a thin laminate for the compression. Won't be able to test it in tension compression. So it must be early tension cycle. But this is interesting chart, which of course in industry, we wanted to use this chart. We would test it and develop our own data. As I've been always emphasizing, industry doesn't believe anything which is published outside the company. We have to test it and validate. This is an interesting chart over here, which I plotted based on the data available. Fatigue strength as a function of percentage 0 degree direction. As I showed previous chart, that as we increase the percentage 0 degree, fatigue strength goes up. So here one can see basically as you are increasing the percentage 0 degree in laminate, your fatigue strength. Fatigue strength is being defined as the endurance limit which is defined normally at 1 million cycle as here. So, okay, parameters affecting composite fatigue. fiber matrix, matrix various properties, percentage 0 degree fiber, layup sequence, thickness of the laminate free edges, environmental conditions, damage conditions, structural details, mode of loading, loading types, tension, compression, loading amplitude, loading frequency. Now I'll show you some charts about the joint fatigue quickly. Again, this is coming from Ogonowski's report, where it shows cyclic peak stress, bearing stress versus number of cycles for effect of R equal to -1 and R equal to 0.1. Normally, what we are doing, in fact, when we are trying to determine the reliable, we would work conservatively and we would determine the endurance limit for R equal to -1 in general, unless one is sure that you never would have R equal to any cycle near R equal to -1 and design with whatever the actual value is. But normally, the practice would be to consider R equal to -1 conservatively when we are considering the endurance limit values. Okay, now this is like again showing the layup effect for various layups as 50, 40, 10, 30, 60. As we have seen from previous results also, that as the percentage 0 degree comes down, the fatigue performance reduces. But here we are dealing with a joint which may be different to the unnosed laminate. But this is data from some reference. It's just schematic data, basically. We won't use it. If we are working in the industry, we'll develop our own data. Although this is from Boeing only, basically, this report was written at McDonnell Douglas, which became Boeing later on. Here's this is effect of the torque. As you can see, we understand if the torque is there, then the joint performance will be better, even in static, and fatigue is even significantly, different to static. 0, pretty low life, and here, good performance. E by D effect, we know that if E by D is more higher, then performance may be slightly improving. Countersink effect, lower performance of the countersink joint, as we understand, compared to non-countersink. Protruded had single shear. So this is the difference between single protruding head fasteners and the countersink. Countersink is lower than protruded head. Durability. Now, this is the durability I defined, but again, I'm trying to define durability here. Durability is the ability of the structure to resist cracking, corrosion, hygrothermal degradation, delamination, wear. Can I spend another 10 minutes or what's the feeling? I want to just.
Yeah, please go ahead, Dr. Garg. Yeah.
Yeah, I'll just close everything to finish up. Okay, so durability effect of a foreign object damage for a specified period. Durability addresses largely economic issue. Durability is economic, of course. Durability, maintenance cost, fatigue, reliability. This is important here now, which I had not shown earlier. The fatigue reliability, that's the critical part of durability. Crack-free for service life of airplane with reliability greater than 95%. This is the requirement from Boeing, which is again provided in those references. And this is why I want to just touch on this one, durability issues. Okay, Boeing requirement is this, and which is very important criteria to understand. Because a couple of weeks back, when I was talking about damage tolerance and fatigue, then the question was, we don't have to worry about, damage tolerance, which will evaluate the inspection intervals. And for composites, we don't have to worry about the durability priorly. Sorry, the damage tolerance approach. Durability, the way Boeing defines metal and composite structures both. For metals also, we have to demonstrate a crack-free service life, which is like a safe life. So first 20 years of service, no significant fatigue cracking in the first 20 years of service. That is probability of cracking of less than 1% with 95% confidence. 30 years of service, more than 30 years of service before fatigue-related maintenance begins to measurably escalate. That is probability of cracking of less than 5% with 95% confidence. So this is the requirement of Boeing that is virtually like a safe life philosophy for 20 years or 30 years here. So that means we have to do the fatigue evaluation and show there is no crack initiation or crack growth at all for the 20 years of service life. So this chart I had shown earlier also, but basically what this shows, the durability and damage tolerance. Both are done to demonstrate the safety of the structures, durability, as well as damage tolerance. Durability shows the safe life for 20 years, no cracking. Damage tolerance provides the residual strength of large damages, as well as the inspection intervals. Inspection intervals for the metal and residual strength, of course, and for composites is essentially the residual strength. But durability has to be shown for both as well. Composites and metal. So durability for compliance for commercial aircraft structures, metals and composites. I've just included here metal just to demonstrate some principles for metals also. Not going into the detail. So durability compliance analysis, that is structural fatigue analysis, environmental and fatigue cycles test, building block approach. I won't go into the details. Coupons, elements, are permanent component for skill test. This spectrum, fatigue spectrum, I've taken from K.R. Fowler. Again, this is Boeing person and in public domain in ASTM, STP. Won't go into detail, I had already shown. And I defined the Geg cycle, which is important to definition. Again, I can repeat the Geg cycle is basically the maximum minimum load for whole of the flight. Say here, minimum load for this one or this one, and maximum load over here. So this will define a Geg cycle. And the way you need to determine Geg cycle can be defined as maximum minimum load for a flight cycle. Total damage in one flight is D flight. Damage in a Geg cycle, D Geg. So Geg damage ratio is determined in D Geg divided by D flight. So number of equivalent Geg cycles per flight and Geg. So N Geg is equal to 1 upon GDR. This is an important concept in the durability analysis or fatigue analysis. So durability analysis metallic details. I just want to show what needs to be done here for the metal and composite quickly. Every aircraft structure detail is analyzed to ensure crack-free design service life on an airplane with reliability 95%. So what happens in design, metal, composite? all the structures will do one DSO and show there is no damage growth. So that's virtually like a safe life. For one DSO, you need to demonstrate there is no fatigue crack growth. Now, somebody has asked a question about this fail-safe and, safe life philosophy and damage-tolerance philosophy. And this is why I want to clarify. All the metallic structures, they need to demonstrate the fatigue life for one DSO, where we don't consider any crack growth at all. So this is very important here.
That means, sir, one DSO is based on the safe life approach.
Yeah, virtually you can call safe life approach, yes. With all the relevant factor of reliability, confidence factor, material factor, and process factor, everything merged together to determine the life. So I've just shown here, I won't go into the details of this. I've just copied from Milan Book 5, this typical chart, so SN chart, don't worry about it. Durability analysis process. Just qualitatively, I have just put up the process here to demonstrate what would you do for durability analysis for the metals. So you have some geometric detail, hole, bolted joint, lug, or any structure detail. You have a spectrum, so define sigma max, sigma min, and Ni. Ni basically, for each of these flight segment, basically you may have several segments, divide the flight into various segments. And for those segments, number of cycles, maximum in stress levels. So you have for each cycle, each of those segment, each of the stress level you will analyze using maximum stress life. So basically, suppose the equation for life is n equal to b 10 to the power a, this logarithmic, where a is a function of stress and stress ratio, b is function of reliability, because this is an ascent curve, which has all the correction factors you need to apply: reliability, confidence, component, material factor, geometry, loading type, processing, environment, number of critical details, KT, etc. I can tell you there are lots of parameters which are used in order to finally develop the reliable ascent curve which are used for the analysis. There are very complex methods available which Boeing had developed. Very standard. And then using this ascent curve, suppose for each of the segment, using the stress level, you determine the DI, basically damage for each of the segment. And total damage of all the segments together would be D. So D gag damage in gag cycle is N gag, N is 1 because one cycle. What is the damage for the one gag cycle is represented by this. N is the life for that stress level for the gag cycle. So gag damage ratio is supposed D gag by D, we defined earlier. Next slide. So what happens now? Suppose you are designing for one DSO. So N flight, that is equal to one DSO. Suppose it's say 50,000 flights. Gag cycle, determine the gag cycle now. S max gag cycle, R of gag is stress ratio for gag. So gag damage ratio, all these are calculated. So N number of equivalent gag cycles would be N flight DSO upon gag. Suppose it's 50,000 flights over here, and gag damage ratio is suppose 0.5. So that means number of equivalent gag cycles will be 100,000 cycles. So using the SN chart, which is after all those reliability and confidence factors available, applicable to that, then you will, for this N gag, from this chart, you will determine what is my maximum reliable stress level. And the fatigue margin then will be represented by Fm equal to S max allowable upon S max gag minus 1. So in summary, this is what needs to be done for metallic structure. There are complex methods developed by Boeing. They are all standard in the handbook with all the parameters. In fact, the experience of like 50, 60 years over that, they have generated all those factors which they have used in order to develop all these reliability and confidence factors, process factor, everything. And then finally, they develop the SN curves factors to determine this life. So this is in summary, a general procedure in order to determine the durability of the structure. So remember this, it's not only the damage tolerance, the durability has to be demonstrated. And damage tolerance is used only for the inspection intervals for the metal. And of course, residual strength. Residual strength is a separate part. So is there any question, about this clarification about this durability and damage tolerance philosophy? Everything is very clearly defined in those papers from Boeing, which you can read. Okay, now for the composite structures, is simple, which I have shown earlier, endurance limit, you generate the SN curve. Again, you use all the reliability factor, confidence factor, material factor, all the loading types, won't go into the details. Suppose this is a final chart. So using this one, you will determine S endurance limit. And then suppose your maximum gag stress, minimum gag stress, R is defined. S endurance limit, basically the SN curve. So FM is FM equal to fatigue margin SN. So this is how we'll demonstrate the durability of the composite structures. Boeing full aircraft fatigue test philosophy. The objective of full-scale aircraft is to verify design service objective. This requirement from FA, which I told last time, to locate areas that may exhibit early fatigue problems, to test. The tests are accelerated relative to field usage so that the corrective action can be made in timely manner, to develop and verify the proposed inspection and maintenance program, to provide effectiveness of design to preclude the possibility of WFD occurring. So basically, is to cover WFD or any surprises which may happen during the testing of the aircraft. That's what is done for.
Hello.
Hello, yes. Hello, yes.
No, sir, please you carry on, sir.
Okay.
Please.
Now, I've just shown in this table, basically 787 was tested for say 165,000 flights, 3.75 short mission objective equivalent to 75 years service. And say Engg 225,000 flights, this teeth. So just an example of how many flights they've used for testing whole of the aircraft. There's a full scale aircraft. Won't go into the details of this. All this for composite, I had already shown. I won't go into details of this one fatigue test of the component, which I had shown earlier during my certification. Durability certification, durability composite certification philosophy, building block approach by testing a small coupons element, which I have discussed earlier. Again, there are many types of this. This type of slide I had shown during certification for the various failure modes which you will have investigated for the durability fatigue testing. Again, I won't discuss. You will generate the required SN curve for required failure mode in order to validate your durability for that failure mode. So this is all very quickly. I've just tried to cover these things. Now, of course, you people must be running out of time now. But if there are any questions, please do ask me. I would really thank all of you to listen to me very patiently. And I thank Professor Dinesh to provide me the opportunity to share my experiences, whatever I could, to all of you. And I wish you a great future in your life. And if you have any issues, any clarification, any questions, you can always send me the email. I would always welcome it. I would appreciate it. I don't mind. So thank you very much. Now, if there are any questions, most welcome.
Thank you very much, sir. I have a couple of queries, sir. I will email you, sir.
Yeah, I think you can send me the email.
Yes, yes.
And if you require any information, reference,
Yes, sir.
I can send you the references. Or anybody else has any question? Any other volunteer? No? Okay. So I think I would have finished now these lectures, but in future, maybe some other topics, I could deliver lectures.
Okay, I guess there are no technical questions. So this is a great opportunity for me, Dr. Garg, to thank you from the bottom of our hearts, because these kinds of topics are very, very difficult to come by in any open literature. Very rarely people from the industry are able to share their knowledge, and you have done such a wonderful balance by sharing what can be shared, legally speaking as well. And you made these things very clear with your disclaimers right in the beginning. But in spite of all of that, I think the knowledge addition has been quite tremendous. We have seen waning attendance in the recent past, but that's probably more because of the other things that the students have been occupied with, and they all know that the recordings are available. So there's been a tremendous response to the recordings as well in terms of the number of people viewing it. And I'm sure this is not just for this current batch, but many future batches will benefit from these recordings, because I see every lecture, apart from the current students, there are lots of our alumni who are participating, who are in the aerospace industry. And that shows the relevance of what you've been speaking for all of their work, current work, as well as future work. So we really thank you once again from the bottoms of our hearts, because this is, there are no words to actually express our gratitude. And you're doing all of this as a voluntary services for free, which is again really, really remarkable. And the way you're going, of course, we know that you'll be going for long, and so we wish you a very, very long innings in terms of good health and life, and the ability to share with many more youngsters and remain young as well. So thank you very much.
Dinesh, can I? Dinesh,
yeah, please go ahead. Yeah.
Can I just take a minute, please?
Yeah, please go ahead.
Am I audible, Dinesh?
Yes, you're very clear.
Yes.
Please go ahead.
Yeah, dear Dr. Garg, I just wanted just a minute with you.
Sure.
Yeah, it has been amazing few weeks of fantastic learning and enlightenment for all of us who have been fortunate to participate in this series of courses. In fact, I haven't seen, heard, or come across anything like this before, where a learned, experienced senior professional has put in so much of time, effort, and energy, so enthusiastically in sharing openly that to all that one has accumulated perhaps over a few decades, and that too for free. So it would have been impossible for any of us to get any of this information which you have shared with us in a few weeks, even if we tried for perhaps several years. And in addition to that, the way you used to make the note of these, questions asked, clarifications, and come back with elaborate, answers satisfactory to that. Has been amazing. So I should say we are really indebted to you, and really don't have words to, say thank you. Just say hats off to you, sir, and we are very fortunate to participate in this. And also, Professor Dinesh, thanks a million for making this happen and coordinating this. Thank you, Garg sir.
Well, thank you all of you. Actually, it has been my privilege that you gave me the opportunity to talk to your students, that I could share my experiences, because I believe the knowledge is something which should always be shared if one can. And when I retired, I took a decision that I would never charge any money for any consultancy, any knowledge sharing. Whosoever wants my help, I'm always willing to do it. And that's why I've been, providing the lecture series to whosoever wants it. And I would keep on doing it as long as organizations are interested in it.
Sir, your fatigue strength and endurance limit is much more than the composite materials, I should say. Please continue this, and wish you very long, very healthy, active, many more years to come.
Well,
thank you.
I think this is keeping me healthy. Otherwise, I would have been in bed by after retirement.
No.
I'm working almost 8 to 10 hours a day every time.
Great.
I'm just looking into a lot of literature. Still, I'm just active, like I'm a researcher, virtually researcher. So anyway, it's pretty late for you people, I think. And thank you very much again. Good evening. And well, let's see if I get opportunity sometime to visit in Bangalore when we come to India. Sometimes we'll visit. Okay. Thank you very much. Goodbye.